Welcome to today's session. We'll be diving into the problem titled Chalkboard XOR game. This is a fascinating problem that combines game theory and bitwise operations. By the end of this discussion, you'll have a deeper understanding of efficient approaches to solve this challenge. Let's get started. In this game, you and your friend take turns choosing numbers from a list called nums. Each turn, the current player selects one number, removes it, and calculates the XOR of the remaining numbers in the list. The critical rule is that if, after calculating the XOR, the result is 0, the player who just made their move loses the game. If the XOR is not 0, the game continues with the other player's turn. The game begins with you, and both players are assumed to play optimally, meaning they make decisions that maximize their chances of winning. Your task is to determine whether you will win the game under these conditions by returning true for a win or false for a loss. Now, let's look at the first example. Here, the input list is nums equals 1, 1, 2. The output is false, which means you will lose if both players play optimally. To see why, the initial XOR of all numbers in the list is calculated as 1 squared equals 2. Since the initial XOR isn't 0, the game proceeds. On your first turn, no matter which number you remove, the XOR of the remaining numbers will be set up in a way that forces you into a losing position. For instance, if you remove 1, 1, the remaining list becomes 1, 2, and their XOR is 1 2 equals 3. Your opponent can then remove the other one, leaving 2, which results in an XOR of 0. This means your opponent wins, and you lose. In the second example, the input is nums equals 1, 2, 3, and the output is true. This time, you win the game. The reason is that the initial XOR of the list is 1 2 cubed equals 0. When the XOR starts as 0, the game is over immediately, and the starting player wins without needing to make a move. In this case, your optimal strategy leads to an automatic win from the beginning. For the third example, with nums equals 5, 1, 1, the output is false. Here, the initial XOR is 5 1 to the power of 1 equals 5, which is not 0, so the game continues. Regardless of which number you remove, the XOR of the remaining numbers will eventually lead to a scenario where your opponent can force you into a losing position, making it impossible for you to win. The constraints for this problem are important to understand. The maximum list size of 1000 ensures that the game involves a manageable number of turns, while the range of values for nums, I, ensures that XOR computations remain efficient. Additionally, the XOR operations' associative and commutative properties play a key role in analyzing the game's behavior. Some edge cases to consider include scenarios like a single-element list, where the first player always loses because the remaining XOR is 0 after their turn. Another edge case is when all elements in the list are identical, leading to predictable XOR patterns. Lastly, for large input sizes, it's crucial to ensure that the solution handles the constraints efficiently without running into performance issues. To start, let's break down the problem and analyze its key components. The essence of the game lies in removing numbers from the array and recalculating the XOR of the remaining elements. Remember, XOR has some unique properties that are critical here. For instance, any number XOR'd with itself results in 0, and XORing any number with 0 leaves the number unchanged. Additionally, the commutative and associative properties of XOR allow us to reorder operations without affecting the outcome. These properties are essential in determining the winner, as the game hinges on the parity of the total XOR value and the number of moves left. A crucial observation is that if the XOR of the entire array is 0 at the start, the first player automatically wins. Otherwise, the strategy becomes dependent on whether the total number of elements in the array is odd or even. Now, we can begin by considering a brute force approach to simulate every possible move in the game. The idea here is straightforward. For each turn, iterate through all elements, remove one, recalculate the XOR, and see if the opponent has no way to win. However, as we'll see, this approach has significant limitations. The brute force approach, while conceptually simple, comes with a major computational cost. The time complexity is factorial, O(n), because we're exploring all possible game states. This exponential growth in possibilities quickly becomes infeasible for large arrays. In terms of space, the recursion stack used to simulate moves requires O(n). While this method helps us understand the structure of the problem, it's far too slow to be practical. To address this, we shift our focus to an optimized approach that leverages mathematical insights. The core realization here is that the first player's ability to force a win depends on the total sum of the array's elements. If the sum is odd, the game dynamics favor the second player because the number of moves available introduces an imbalance. On the other hand, if the sum is even, the first player gains an inherent advantage. This observation allows us to bypass exhaustive simulations and focus directly on the game's higher-level structure. With this mathematical insight in mind, we can outline a much more efficient algorithm. First, calculate the XOR of the array and the sum of its elements. If the XOR of the entire array is 0, the first player wins immediately because there's no way for the second player to force a change in the game state. If not, the game outcome depends on the length of the array. When the length is even, the first player can always maintain control and secure a win. Conversely, if the length is odd, the second player has the advantage. This algorithm is remarkably efficient, with a time complexity of O(n) to compute both XOR and sum, and a constant space requirement of O(1). While it's elegant and avoids unnecessary computation, this approach relies heavily on mathematical reasoning. Beginners might find it less intuitive compared to the brute force method, which explicitly simulates moves. Still, its efficiency makes it the clear choice for solving the problem at scale. Given these considerations, the optimized mathematical approach stands out as the preferred solution. It's efficient, elegant, and directly leverages the key properties of XOR and the problem's structure. While the brute force method is easier to conceptualize initially, its factorial time complexity makes it impractical for larger inputs. By using the mathematical insight, we reduce the problem to a few quick calculations and a simple decision based on parity. This strategy focuses on the XOR of the array, the sum of its elements, and the parity of the array's length, allowing us to determine the winner in constant time after an initial O(n) pre-processing step. This combination of efficiency and clarity makes it the ideal solution for both small and large inputs, ensuring scalability without sacrificing logical rigor. To tackle the Chalkboard XOR game, we start by breaking down the algorithm into manageable steps. First, we need to understand the problem requirements. The input is an array of integers, and the task is to calculate the XOR of the remaining elements after removing each element from the array. Depending on the problem, we might either return the list of XOR results or perform further operations. It's also important to consider constraints, such as handling edge cases where the array has only one element, all elements are identical, or some elements are negative. Next, we make key observations about XOR properties. For instance, a number XOR'd with itself results in 0, and XOR with 0 leaves the number unchanged. Additionally, XOR is both commutative and associative, meaning we can rearrange the operations without changing the result. Lastly, we introduce the idea of pre-computing the XOR of the entire array, which we'll call total XOR. This pre-computed value serves as the baseline XOR when no element is removed, significantly optimizing the solution. Now that we've pre-computed total XOR, we can move on to iterating through the array. For each element in the array, we calculate the XOR of the remaining elements using the formula remaining XOR equals totals or XOR ARR(I). This formula works because removing an element is mathematically equivalent to reversing its contribution to the XOR. Once we compute the remaining XOR for an element, we append it to a results list. After processing all elements, the results list contains the XOR values for every possible removal. Depending on the problem's requirements, we can then either return this list or perform additional operations, such as finding the maximum XOR or summing all the XOR values. The key insight here is the efficiency gained through pre-computation. Instead of recalculating the XOR for the remaining n1 elements repeatedly, which would take O(n²) time, using total XOR reduces the overall complexity to O(n). This optimization is a direct application of XOR's commutative and associative properties, allowing us to reverse a numbers effect with a simple calculation. When implementing this algorithm, it's essential to handle edge cases appropriately. For example, if the array contains only one element, there are no remaining elements after removal, so the result might be an empty array or a predefined fallback value. If all elements in the array are the same, the remaining XOR will be identical for every removal since the array's symmetry ensures the same result each time. For arrays with negative numbers, the algorithm works seamlessly because XOR operates at the bit level, and it doesn't distinguish between positive and negative values. The data structures we use include the input array itself, a results list to store XOR values after each removal, and a single integer, total XOR, which holds the pre-computed XOR of all elements. This approach minimizes redundant calculations, ensuring that the algorithm is both time and space efficient. Specifically, the time complexity is O(n), as we process the array in two linear passes, one for calculating total XOR and another for computing remaining XOR. The space complexity is also O(n), accounting for the input array and the results list. Now let's look at the pseudocode implementation of the algorithm. We start by defining a function that takes the input array, ARR. First, we calculate total XOR by iterating over all elements in the array and applying the XOR operation to accumulate their values. This pre-computed XOR serves as a baseline for the subsequent calculations. Next, we initialize an empty results list. Then, for each element in the array, we compute remaining XOR by XORing total XOR with the current element. This effectively removes the element's contribution from the total XOR. We append the resulting value to the results list. Finally, after iterating through all elements, we return the results list. This pseudocode encapsulates the efficient logic we discussed, leveraging pre-computation and the properties of XOR to achieve linear time complexity. To illustrate the algorithm, consider the input array 3, 5, 7. First, we compute total XOR by XORing all elements together, 3 XOR 5 XOR 7, which equals 1. Next, we calculate the remaining XOR for each element. Removing 3 gives 1 XOR 3 equals 2, removing 5 gives 1 XOR 5 equals 4, and removing 7 gives 1 XOR 7 equals 6. This results in the list 2, 4, 6. For an edge case, think about an array like 0, 0, 0. Here, the total XOR is 0, and removing any element still leaves the XOR unchanged at 0. Thus, the results list becomes 0, 0, 0. These examples demonstrate how the algorithm handles both typical cases and edge cases efficiently, ensuring correctness across a variety of inputs. This is the solution to LeetCode problem number 810, Chalkboard XOR game. The problem revolves around determining if Alice can always win given the rules of the game. Let's break down the solution step by step. First, the function XOR game is defined, taking a list of integers nums as input. The goal is to calculate the XOR of all elements in the list. This is achieved using the variable total underscore XOR, which starts at 0 and iteratively XORs each number in nums. XOR is a binary operation that toggles bits. If two bits are the same, the result is 0, otherwise, it is 1. The next step is to determine the outcome based on two key observations. 1. If the XOR of all numbers, total underscore XOR, is 0, Alice wins immediately because she can always remove an element to maintain the XOR as 0. This is because XOR of 0 with any number is the number itself, so she can maintain favorable conditions. 2. If the length of the array is even, Alice can also win. This is because, in an even-length game, each player gets an equal number of turns, and Alice can force Bob into a losing position if the XOR is non-zero. Finally, the function returns true if either of these conditions is met, the XOR is 0, total underscore XOR equals 0, or the array length is even, len, nums, %2 equals 0. Otherwise, it returns false, meaning Alice cannot guarantee a win. This algorithm works efficiently in O(n) due to the single loop for calculating the XOR. It also uses O(1) additional space, making it optimal for the problem constraints. Edge cases, such as an empty list or a single element, are implicitly handled by the algorithm's logic. This is the Java implementation for LeetCode problem number 810, Chalkboard XOR game. The logic mirrors the Python solution, where we calculate the XOR of all elements in the input array and determine the result based on the XOR value and array length. Key differences include Java's use of type declarations and enhanced for loops for iterating arrays. In this example, we start with the array nums equals 1, 1, 2. The first step is to calculate the XOR of all elements in the array. We initialize total underscore XOR to 0 and then process each number in the array. For the first number, 1, we compute 0 XOR 1, which results in 1. Next, for the second number, also 1, we compute 1 XOR 1, which gives 0. Finally, for the third number, 2, we compute 0 XOR 2, resulting in 2. After looping through all the elements, total underscore XOR is equal to 2. Now, we evaluate the conditions. First, we check if total underscore XOR is 0. It's not, since total underscore XOR equals 2. Then, we check if the length of nums is even. The length is 3, so it's odd. Since neither condition is satisfied, Alice loses this game, and the output is false. Here, the array is nums equals 3, 3, 3, 3. Again, we begin by calculating the XOR of all elements. Starting with total underscore XOR initialized to 0, we process the first number, 3, and compute 0 XOR 3, which equals 3. For the second number, also 3, we compute 3 XOR 3, which results in 0. For the third number, 3, we compute 0 XOR 3, giving 3. Finally, for the fourth number, 3, we compute 3 XOR 3, which results in 0. After processing all elements, total underscore XOR is 0. Now, let's evaluate the conditions. The first condition asks if total underscore XOR is 0, and in this case, it is. Because this condition is true, Alice wins the game, and the output is true. This time, the array is nums equals 5, 1, 1, 1. As usual, we begin by calculating the XOR of all elements. Starting with total underscore XOR initialized to 0, we process the first number, 5, and compute 0 XOR 5, which equals 5. Next, for the second number, 1, we compute 5 XOR 1, resulting in 4. For the third number, 1, we compute 4 XOR 1, which gives 5. Finally, for the fourth number, 1, we compute 5 XOR 1, resulting in 4. After processing all numbers, total underscore XOR equals 4. Now, we evaluate the conditions. First, we check if total underscore XOR is 0. It's not, since total underscore XOR equals 4. Next, we check if the length of nums is even. The length is 4, which is even. Since the second condition is satisfied, Alice wins this game, and the output is true. Here, we analyze the time complexity of the XOR game function by breaking it into its components. First, the XOR computation loop iterates over every element in the array nums, calculating the XOR of all elements. Since this loop runs exactly n times, where n is the length of the array, and each XOR operation takes constant time, the cost of this loop is O(n). After computing the XOR, the function performs two checks, whether total underscore XOR equals 0, and whether the length of the array is even. Both of these operations involve simple constant time calculations, such as equality comparison and modulo operations, which add an O(1) cost. Therefore, the overall time complexity is dominated by the O(n) cost of the XOR computation loop. Now that we've identified the dominant term, we can conclude that the overall time complexity of the XOR game function is O(n). Shifting our focus to space complexity, the analysis is straightforward. The function does not modify or duplicate the input array nums, meaning it doesn't use any additional data structures to store elements. The input space, O(n), is provided externally and does not count toward auxiliary space usage. The function only requires a single integer variable, total underscore XOR, to store the XOR of all elements, which takes constant space. Thus, the auxiliary space usage is O(1). Given the lack of additional data structures and the use of only constant space variables, the overall space complexity of the algorithm is O(1). When comparing this approach to a naive or brute force solution, the advantages become clear. A brute force method might involve simulating the game by repeatedly removing elements from the array and recalculating the XOR each time. This would lead to multiple iterations and potentially quadratic time complexity, O(n squared, or worse. The optimized solution avoids this by leveraging mathematical insights, such as the fact that if the XOR of all elements is 0, Alice can win immediately, and if the array length is even, Alice has a guaranteed strategy. These observations allow the algorithm to achieve linear time complexity by computing the XOR in a single pass. Finally, let's analyze the function's behavior in different scenarios. In the best case, if total_XOR is 0, the function terminates immediately after computing the XOR of the array. Even in this case, the XOR computation loop takes O(n). In the average case, the function still performs the XOR computation and the constant time conditional checks, resulting in O(n) complexity. In the worst case, the function computes the XOR of all elements without early termination, but the complexity remains O(n), as the XOR loop is the only non-constant operation. Across all cases best, average, and worst, the time complexity is linear, O(n), while the space complexity remains constant, O(1). When tackling XOR problems, it's crucial to avoid common mistakes that can complicate your solution. First, many beginners ignore the core properties of XOR, such as a XOR A equals 0 and a XOR 0 equals A. These properties are foundational and can greatly simplify your logic. For example, you can use them to cancel out duplicate elements or reduce operations. Next, misunderstanding XOR's behavior in sequences can lead to errors. Remember, XOR is both associative and commutative, meaning the order of operations doesn't matter. This is especially important when working with prefix or cumulative XOR calculations. Another frequent issue is overcomplicating the solution with nested loops. While it might seem straightforward to approach the problem with an O(n²) or O(n³ solution, these approaches are inefficient and fail on larger test cases. Instead, you should aim for a more scalable O(n) solution when the problem involves cumulative XOR. Lastly, edge cases like empty arrays, single-element arrays, or arrays with identical elements often get overlooked. These scenarios can break an otherwise correct solution, so always test for them explicitly. Another common pitfall is confusing XOR with arithmetic operations like addition or subtraction. XOR is a bitwise operation and doesn't follow the same rules as arithmetic. For instance, assuming that a XOR B XOR C is equivalent to a plus B plus C is a fundamental mistake that can derail your solution. Recognizing the unique properties of XOR is critical, especially in interview settings. Interviewers often design XOR problems to test both your understanding of these properties and your ability to exploit them effectively. Additionally, scalability is key in interviews. Efficient solutions that utilize techniques like prefix XOR to achieve O(n) time complexity are highly valued. Brute force approaches should only be used if explicitly called for. Lastly, addressing edge cases proactively during an interview demonstrates strong problem-solving skills. For example, explaining how your solution handles empty arrays or arrays with duplicate elements shows that you've thought through the problem comprehensively. Identifying and communicating patterns in XOR operations is another important skill. If you notice a repeating pattern or property, articulate it clearly. For example, explaining how the XOR of a range can be derived from prefix XORs demonstrates a deep understanding of the concept. This is especially useful in problems where cumulative calculations are required. Speaking of related problems, XOR concepts appear frequently in LeetCode challenges. For instance, problem 136, single number, involves finding the single non-duplicate number in an array where every other number appears twice. Similarly, problem 260, single number 3, asks you to find two non-duplicate numbers under the same conditions. Problem 1310, XOR queries of a subarray, tests your ability to use prefix XOR to solve subarray queries efficiently. Lastly, problem 421, maximum XOR of two numbers in an array, introduces a more advanced concept involving a tree-based solution to maximize XOR pairs. Practicing these problems can help you master XOR techniques and prepare you for similar challenges. When solving XOR problems, it's helpful to understand the trade-offs between different approaches. The brute force method involves comparing all pairs or subsets directly to calculate XOR values. While this approach is simple and easy to implement, it suffers from high time complexity, often O(n²), or worse, making it impractical for larger input sizes. A more efficient approach involves using prefix XOR. This technique allows you to compute cumulative XOR values efficiently, reducing the time complexity to O(n). However, it does require additional space to store the prefix XORs, which is a minor trade-off for the significant performance gains. For more advanced XOR problems, such as maximizing XOR pairs, a bitwise tree can be used. This structure stores the binary representations of numbers, enabling fast XOR computations. While tree-based solutions are highly efficient, they are more complex to implement and may not be necessary for simpler problems. By understanding these approaches and their trade-offs, you can choose the most suitable method for any XOR-related challenge. That's a wrap. We covered the Chalkboard XOR game, breaking down the problem and exploring key strategies. Remember the importance of XOR properties in game theory techniques. Thanks for joining, and don't forget to like, comment, and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!